The black water heaved 10 feet below the belly of the Wellington. The pilot, eyes straining through the windscreen, saw nothing but the faint white caps of a moonless Atlantic swell. Behind him, the radar operator stared at the cathode tube, watching a single green pip brighten and hold steady against the sea clutter. It was a U-boat, surfaced and running hard for the convoy lanes, its diesels churning a wake that no human eye could see in this darkness. The operator called the range. The navigator punched numbers into his computer, and the captain began a gentle turn to starboard, lining up the invisible target. Then the searchlight operator threw a switch, and a billion candle power of raw white light stabbed down from the aircraft's belly, pinning the submarine in a circle of brilliance that turned night into noon. They marked the position and shut down the light. The aircraft turned for home, leaving a spreading slick of oil and floating debris, the wreckage of 100,000 hours of Allied engineering. Yet, within weeks of the first shots, the Royal Navy understood a new reality. This fragile machine might be the only answer to a weapon that threatened to strangle the British Isles. The submarine had arrived. On the 5th of September, Korvettenkapitän Hersing in U-21 sank the light cruiser HMS Pathfinder off St. Abb's Head. 17 days later, Lieutenant Weddigen in U-29 destroyed 3 armoured cruisers, Aboukir, Cressy and Hogue, in a single hour. The Admiralty, its confidence in battleship gunnery shaken, began casting about for any means of hunting the invisible killer that cruised beneath the waves. The airmen of the Royal Naval Air Service stepped forward, carrying bombs that weighed less than a deck gun shell and flying machines that could barely lift a pilot, let alone a weapon that could crack a pressure hull. In early 1915, the carrier Ben Maitri steamed into the Aegean, her deck loaded with short 184 seaplanes. These were biplanes with fabric-covered wings spanning 63 feet, powered by a single Sunbeam engine, generating 225 horsepower. They were slow, vulnerable, and loaded with a weapon that had never been tested in combat from the air. 14-inch torpedoes slung between the floats, weighing half a ton. On the 3rd of April, Flight Commander Charles Edmonds took off, spotted a Turkish supply ship dead in the water after a submarine attack, and dropped his torpedo from low altitude. The weapon ran straight and true, detonating against the hull and sending the vessel to the bottom. 5 days later, Flight Lieutenant Dacre, forced down by engine trouble, taxied his seaplane toward a Turkish tug, launched his torpedo from the waterline, and sank it. The airborne torpedo attack had been born, but the weapon was small and the aircraft underpowered. The Royal Navy's battleship admirals were not yet convinced that the flying machine was anything more than a scout. The real crisis was not surface raiders, it was the submarine. By 1917, U-boats were sinking 800,000 tons of British shipping every month. The convoy system, reintroduced after centuries of neglect, began to choke off the slaughter, but the escorts needed eyes in the sky. Aircraft could force a U-boat to submerge, preventing it from reaching its attack position or surfacing to recharge batteries. Yet, when an aircraft caught a boat on the surface, the weapons it carried were almost useless. The standard anti-submarine bomb weighed 100 pounds and contained a charge of amatol that required a direct hit to cause fatal damage. Its thin steel casing, designed to fragment against the deck of a surface ship, simply bounced off the curved pressure hull of a submerged U-boat. A near miss within 6 feet might crack a weld or jam a hydroplane, but it would not flood the boat. The aircrews knew this. They attacked anyway, straddling their targets with bombs that peppered the sea like hailstones on a tin roof, hoping for a lucky strike. The Admiralty, grasping for a solution, adopted a tactic born of desperation. In April 1918, 7 flights of surplus de Havilland DH-6 trainers were organized into special duty squadrons and dispatched to coastal airfields from Cornwall to the Shetlands. The DH-6 was a slow, docile machine designed to teach student pilots, with a top speed of 66 miles per hour and an endurance of just over 3 hours. Now it was pressed into service as a submarine hunter, painted in drab camouflage and loaded with a single 100-pound bomb. The flights were called Scarecrow patrols, and the logic was brutally simple. Any submarine captain who sighted an aircraft would dive, regardless of whether the aircraft was armed. The U-boat would then be forced to run on batteries, its speed cut to 8 knots, its range slashed to 60 miles. It could not recharge, it could not pursue a convoy, and it could not fight. The DH-6s flew thousands of hours along the shipping lanes, and sinkings plummeted. The tactic worked, but it was a stopgap, a desperate improvisation that proved only that the aeroplane could harass the submarine, not kill it. The armistice brought silence over the Western Front and the North Sea, but it also brought a political edict that would cripple British maritime aviation for 2 decades. The government adopted a 10-year rule, a rolling assumption that no major war would occur for a decade. Funding for the Royal Air Force collapsed. The coastal squadrons that had patrolled the sea lanes were disbanded, their flying boats scrapped or sold, their aircrews demobilized. The Royal Naval Air Service, which had pioneered anti-submarine tactics, was absorbed into the new Royal Air Force in April 1918. Senior naval aviators who understood the sea were sidelined or forced to retire. The Admiralty, stripped of its air arm, returned to its faith in battleship, gunnery and ASDIC, the sonic detection system that promised to make the submarine obsolete. No one developed a practical airborne depth charge. No one built a purpose-built maritime patrol aircraft. The lessons of the U-boat war were sealed in archives, unread and forgotten. On the 14th of July 1936, the Air Ministry issued the order that created Coastal Command. Air Marshal Sir Arthur Longmore assumed command at Lyon-Solent, inheriting a force of 13 squadrons scattered across the United Kingdom and the Mediterranean. His frontline aircraft were biplane flying boats, supermarine Stranraers with fabric-covered wings and open-gun cockpits, Saro Londons that cruised at 137 miles per hour, and short Singapores powered by 4 engines mounted in push-pull pairs between the wings. These were machines designed in the 1920s, built for colonial patrols in calm tropical waters, not for the gale-swept North Atlantic. Their crews were brave and skilled, but their weapons were unchanged from the previous war. The standard anti-submarine bomb still weighed 100 pounds. It still required a direct hit. It still could not breach a pressure hull. The Stranraer carried 4 of these bombs in racks beneath its lower wing, a payload that represented the sum total of British airborne anti-submarine lethality. Alongside the flying boats, the command fielded a new land plane that would become its workhorse for the first 2 years of the coming war. The Avro Anson Mark I was a twin-engined monoplane with a wingspan of 56 feet, powered by 2 Armstrong Siddeley Cheetah engines generating 350 horsepower each. It cruised at 170 miles per hour and carried a crew of 3, a pilot, a navigator, and a wireless operator doubling as a gunner. Its armament consisted of a fixed forward-firing Vickers machine gun, operated by the pilot, and a single Lewis gun in a dorsal turret. The bomb bay held 2 100-pound anti-submarine bombs, with external racks for 8 20-pound bombs or flares. The Anson was reliable, stable in flight, and utterly obsolete as a combat aircraft. Its range of 600 miles gave it barely enough endurance to escort a convoy 200 miles into the Atlantic before turning for home. The deadly mid-ocean gap, where no land-based aircraft could reach, yawned open and undefended. In 1937, Air Chief Marshal Frederick Bowhill relieved Longmore and moved the command headquarters to Northwood in Middlesex. Bowhill had served as a midshipman in the Royal Navy before transferring to the Royal Naval Air Service, and he understood the sea in his bones. He established joint operations rooms where Royal Air Force and Royal Navy officers worked side by side, sharing intelligence and coordinating patrols. It was a crucial innovation, but it could not compensate for the hardware that was missing. The command still had no depth charge adapted for aerial delivery. The Mark VII naval depth charge, with its hydrostatic pistol and 300 pounds of torpegs, existed in shipboard inventories, but no one had designed a fairing and fin assembly to allow it to be dropped from an aircraft. The 100-pound bomb remained the primary anti-submarine weapon. Coastal Command had the men, the aircraft, and the will to fight. But as the German Wehrmacht massed on the Polish frontier, it did not yet possess the means to sink a U-boat. The foundations had been laid. The tools had not arrived. After the accidental bombing of HMS Snapper by a 100-pound bomb in December 1939, the Admiralty finally initiated development of an air-droppable depth charge. The Mark VII naval depth charge, with its 300-pound Torpex charge and hydrostatic pistol, was the obvious candidate, but its cylindrical steel body tumbled and broke up when released from a bomb bay at 200 miles per hour. Engineers at the Royal Ordnance Workshop solved this by riveting a conical nose fairing to the front and bolting 4 stabilizing fins to the rear. The first prototype was ready for testing in early 1940, and Coastal Command at last had a weapon that could crack a submarine's pressure hull. The first test drop over the Solent in late spring went poorly. The fairing crumpled under the slipstream force, causing the depth charge to cartwheel into the grey sea and detonate prematurely at the preset depth of 25 feet. The workshop crew hauled a replacement casing back to the bench and braced the fairing with a reinforcing collar, then re-welded the fins with a thicker bead. A second test 3 weeks later succeeded. The weapon entered the water cleanly, sinking at 8 feet per second with 35 feet of underwater forward travel, precisely as the diagrams had predicted. The development of an aerial depth charge did not begin until after a friendly fire incident in December 1939, when an Anson dropped a 100-pound bomb on HMS Snapper. The urgent work to adapt the Mark VII naval weapon continued through the spring and early summer of the following year. By August 1940, the first production weapons with reinforced nose fairings and stabilizing fins reached the operational squadrons in Northern Ireland. A No. 233 Squadron Hudson, patrolling the northwest approaches in late September, sighted a U-boat crash diving and released a 4-charge stick. The crew saw an eruption of white water and a brief oil slick, though a kill was not confirmed. Coastal Command now had a weapon that could inflict lethal damage beneath the surface. By late November 1939, the first production ASV Mark I radar sets began replacing the jury-rig prototypes, and over the following weeks 12 Hudsons from NOAA's 220, 224, and 233 squadrons were fitted with the new installation in the nose compartment. The transmitter dipoles jutted forward above the pilot's canopy, and the receiver aerials were bolted under each wing, while a cathode ray tube indicator sat on a shelf next to the wireless operator. Operating at 214 MHz, the set could, in theory, detect a surfaced U-boat at 5.5 miles from 3,000 feet. In practice, the returns were messy. The operators had to interpret a wavering vertical trace while the aircraft bounced through North Sea troughs. The radar's fatal flaw emerged within the first month of operation. At ranges below half a mile, the energy reflected back from the wave crests drowned the target blip entirely, creating a hard, blind zone. A Hudson from No. 224 Squadron closed on a contact in December, the operator counting down the range until the trace dissolved into pulsating sea clutter. The pilot held course on dead reckoning for 90 breathless seconds, but the U-boat had dived. The radar's reliability also proved poor. The klystron tube drifted in the freezing airflow, and the transmitter failed intermittently, leaving crews to fall back on the Mk1 eyeball. On the 30th of January 1940, Flying Officer Edward Brooks of No. 228 Squadron lifted his Sunderland off the water at Pembroke Dock and headed toward the Scilly Isles. His crew carried 250-pound anti-submarine bombs, not the new depth charges, and their search relied entirely on visual lookout. They received a signal from the sloop HMS Fowey, which had depth-charged a U-boat after it torpedoed a tanker. Brooks spotted the boat first, U-55 wallowing on the surface with damaged steering gear, unable to submerge, its deck gun firing wildly at the approaching flying boat. Brooks dropped his bombs in a textbook straddle, and the submarine settled by the stern and sank. Summer brought the Mediterranean into full combat, and Flight Lieutenant W. W. Campbell of No. 230 Squadron flew his Sunderland out of Alexandria on the 28th of June. The water was clearer here than in the Atlantic, and Campbell spotted a periscope feather from just 1,000 feet. He lined up and released two 250-pound bombs. The bow of the Argonauta rose vertically and then slid down beneath the surface in a royal of oil and debris. The next day, Campbell repeated the performance, sinking the Rubino and then landing his Sunderland in a rising swell to pull 4 Italian survivors from the water, a dual victory that earned him the Distinguished Flying Cross. Further west, Flight Lieutenant W. Gibson of No. 10 Squadron Royal Australian Air Force was defending a convoy when a straggler was torpedoed out of position. Gibson quartered the area for hours before finding U-26 surfacing to escape the corvette HMS Gladiolus. His 4 depth charges hammered the boat, blowing it upward and forcing the crew to abandon ship. The destroyer HMS Rochester pulled 48 German sailors from the sea. Yet for every U-boat caught near the convoy, more slipped through the widening gap between the escort front and mid-ocean, where no land-based aircraft could reach. The fall of France in June 1940 transformed the strategic geometry. Biscay ports now gave U-boats direct access to the western approaches, and transit times shortened by weeks. Within Coastal Command headquarters at Northwood, an administrative officer named Humphrey de Verde Lee heard the daily loss reports from the convoy escort squadrons. He had served as a pilot in the previous war, flying anti-submarine patrols himself, and he understood the tactical problem. The ASV radar could find the enemy, but no pilot could see the target in those final critical moments. Lee began drawing sketches of a searchlight mounted in an aircraft's belly, powered by a generator strong enough to turn night into day. The Air Ministry dismissed the concept immediately, citing the weight and drag of such a massive illuminant and pointing to failed tests from 1928. Lee, undeterred, located a DWI Wellington, fitted with a high-output generator, originally designed to explode magnetic mines. He scrounged a naval searchlight, cut an aperture in the Wellington's fuselage floor, and wired the generator to the lamp. The beam, when tested on a static ground rig, burned a column of white light visible for miles. The next hurdle was the man in charge of procurement, Philippe Joubert de la Ferte, who initially backed a competing design, the Helmore light, before reversing his position once its flaws became undeniable. In May 1941, the test aircraft flew its first nighttime trial over the darkened English Channel. The pilot descended to 100 feet, aligned the nose with a floating target raft, and activated the searchlight. The beam punched through the mist and illuminated the raft with such intensity that the test observer could now count the individual oil drums lashed to its frame. Lee stood on the airfield perimeter watching the glow on the horizon, and, as the aircraft landed, he could see the scorched paint around the light housing and the strained metal fasteners still holding. The concept had been proven. No one, 7-2 Squadron, was selected to take the Lee Light into combat, the crews converting from their standard Wellingtons to the modified Mark 7.8s. The pilots distrusted the extra drag, which reduced airspeed by 15 knots and made the aircraft nose-heavy during the attack run. The gunners, meanwhile, had to learn to keep their turrets clear of the beam's backscatter, which could blind them at the moment of weapons release. Training flights over Cardigan Bay continued through the summer, the Wellingtons roaring in at wave-top height, switching on the light only in the final 10 seconds to simulate a surprise night attack. The first operational trial came in November, when a number 7-2 Squadron Wellington on Biscay patrol picked up a radar contact on an overcast night with zero moonlight. The operator guided the pilot down the bearing, counting the range, until the trace vanished into the sea return at half a mile. The captain called for the light, and the beam snapped on to reveal U-68 fully surfaced, its conning tower watch frozen in the act of raising binoculars. 4 depth charges tumbled from the bomb bay, and the Wellington pulled up hard, the tail gunner watching the roiling water where the submarine had been. The boat survived, but its captain later reported that the attack had come without a single second of warning. By December 1941, the combined headquarters at Northwood was coordinating Lee Light patrols alongside standard daylight sweeps, but the mid-ocean gap remained a yawning wound. Convoys crossing south of Iceland and west of the 20th meridian entered a zone of total darkness and total isolation, where U-boats operated on the surface in daytime without fear of aircraft. The adapted depth charge and the new searchlight were both stopgaps, brilliant and necessary, but stopgaps nonetheless. Furter, now the air officer commanding-in-chief, had already initiated an urgent priority request for a radar immune to German detectors. Radio wave that could see in the dark without being heard. In a laboratory in Birmingham, a device called the cavity magnetron had just generated 500 watts at a frequency of 3 billion cycles per second. A stream of microwave energy that would slice through the night like a scalpel. The race was now between the scientists in British labs and the engineers in German shipyards, and the Atlantic would be the proving ground. The winter of 1942 found the Coastal Command operations rooms tense with a new kind of silence. Aircraft were returning from Biscay patrols with empty bomb bays and no sightings to report. Not because the U-boats had vanished, but because they were diving 20 minutes before the Wellingtons arrived overhead. The metric radar pulses from the ASV Mark II sets were traveling out across the water, and the German boats were hearing every one of them, their new receivers lighting up in the radio compartments like early warning beacons. The convoys were still losing ships in the mid-Atlantic gap, beyond the reach of any land-based aircraft, and the Lee Light squadrons were finding fewer surface targets each week. The cavity magnetron had pulsed its first microwave energy in a Birmingham laboratory months earlier, but turning that laboratory demonstration into a working airborne radar set remained a grinding industrial challenge. The valve itself was a solid copper block, drilled with 6 precisely machined cavities, each one a resonant chamber that forced electrons to oscillate at 3 billion cycles per second, generating a beam of 10-centimeter radio waves. No German detector could hear those frequencies because no German scientist believed such short waves could carry enough power to reflect off a ship. The magnetron was the key, but the lock it would open had not yet been forged into a complete radar system. The physicists at the telecommunications research establishment worked through the winter to build an airborne transmitter around the new valve, struggling with components never designed for microwave frequencies. The waveguides were copper pipes polished to mirror smoothness inside, because any roughness would scatter the energy before it reached the antenna. The receiver crystals were laboratory-grown silicon pressed into tiny brass holders, each one tested and discarded if its sensitivity fell below the threshold. Every element of the system had to be invented from scratch, and every week the production engineers found new failure points that sent the physicists back to their benches. The Germans, meanwhile, had solved their own technical problem with far cruder materials. The Metox R600 receiver itself was based on a captured French design, a black box of vacuum tubes and tuning circuits that could sweep the metric wavelengths where ASV Mark II transmitted its searching pulses. What the U-boat crews lacked was an adequate aerial, so the dockyard welders at Lorient fabricated a crossframe from scrap timber and strung it with antenna cables salvaged from damaged boats. The Biscayakroids, the Biscay Cross, was a rough wooden crucifix mounted on a bracket welded to the periscope stanchion, and the watch officer rotated it by hand, listening through the boat's loudspeaker system for the rising whine of an approaching aircraft. The wooden cross was a brutal piece of improvisation that worked. When a Metox-equipped U-boat surfaced in the Bay of Biscay to recharge its batteries, the cross came up through the conning tower hatch, and a rating clamped it to its bracket, the coaxial cables snaking down into the radio room. The operator donned headphones and swept the frequency band, and if an ASV Mark II pulse struck the antenna, the entire crew heard it through the boat's amplifiers. A sharp electronic note that meant dive now, no delay, no waiting to identify the bearing. The U-boats were submerging before the Coastal Command aircraft ever saw them on their radar screens. The consequence rippled through every Allied patrol report that summer. Sightings per sortie fell by more than half between June and August, and attacks on surfaced submarines became rare events, celebrated in operations rooms with the same relief as a confirmed kill. The Lee Light Wellingtons of No. 172 Squadron, which had been the command's great hope for night attacks, were now illuminating empty water, where the U-boat had been 20 minutes earlier. The mid-ocean gap remained a killing ground for merchant seamen, and the small escort carriers that might close it were still months away from deployment. Something had to break the cycle. The something was being assembled in a hangar at Deptford, where the prototype ASV Mark III radar was being fitted into a Wellington bomber for flight trials. The installation was dramatically different from the earlier metric sets. Instead of a forest of dipole aerials bolted to the fuselage and wings, the centimetric radar used a single rotating dish scanner housed inside a streamlined blister beneath the belly. Spinning eye that painted a sharp electronic picture of the sea surface without radiating sideways lobes that a detector could pick up. The operator in the fuselage saw a plan position display, a circular screen where contacts appeared as bright specks and land masses showed their contours. It was a revolution in clarity, and it was invisible to the Metox. The manufacturing challenge was immense. Each ASV Mark III set required a magnetron machine to tolerances measured in thousandths of an inch, and the machine tools to produce them in quantity barely existed outside the specialized workshops of the Atomic Research Establishment. The Air Ministry allocated production priority to night fighter radars first, arguing that the defense of British cities against renewed Luftwaffe bombing took precedence over the Bay of Biscay. The argument raged through Whitehall committees, while the operational command marked time with its increasingly blind metric sets, and the U-boats sailed beneath an electronic silence that protected them more effectively than any armor plate. Furter pressed the case from northward with a bluntness that frayed tempers in the Air Ministry's technical branches. He pointed to the rising tonnage figures, the tankers burning off Trinidad, the convoy battles in the Gap, where Coastal Command aircraft never flew because they could not reach that far. The answer, he argued, was not just the centimetric radar but the very long-range aircraft to carry it, the Consolidated Liberator with its 4 engines and its fuel tanks in the wings that could keep a crew airborne for 17 hours. The Americans were building them in numbers, but Bomber Command wanted every heavy airframe for the strategic offensive, and the allocation committee was not yet convinced that a handful of maritime squadrons could change the balance in the Atlantic. By late autumn, the first production ASV Mark III sets were trickling out of the factories, each one a numbered asset tracked on a board in the operations room at Northwood. The decision was made to equip the Lee Light Wellingtons first, because their night patrols over Biscay offered the cleanest test of the new radar's immunity to METOX. The crews of No. 172 Squadron began converting to the Mark III sets in November, learning to interpret the new plan position displays with their sharp contacts and their absence of the sea clutter that had blinded the metric sets. The first operational sorties were flown in December, and the sighting rate began to climb before anyone dared to declare the U-boat detector defeated. The reaction on the other side of the water was confusion. U-boat commanders who had trusted their METOX warning to give them 10 minutes to submerge were suddenly being illuminated by searchlights with no preceding electronic warning at all. On Christmas Eve 1942, a No. 172 Squadron Wellington caught a Type 7 boat on the surface 200 miles west of Brest, the ASV Mark III operator tracking the contact down to half a mile, while the METOX in the submarine remained utterly silent. The searchlight snapped on at 800 yards. The depth charges fell in a straddle, and the U-boat vanished in a boil of foam and oil that spread across the black Atlantic water. The window of surprise was narrow, and the command knew it. German signals intelligence would eventually deduce that the British had shifted to centimetric frequencies, and when they did, the laboratories at Telefunken and Siemens would begin building a new detector. The race was between the rate at which the ASV Mark III sets could be produced and the speed with which the German electronics industry could design and manufacture a countermeasure. The winter of 1942 gave the Allies a temporary advantage, measured in weeks rather than months, and every available aircraft had to be thrown into the fight before the balance shifted again. That logic drove the planning for Operation Gondola, conceived in late January 1943 as a saturation offensive across the U-boat transit routes in the central Bay of Biscay. The assault would use every available centimetric-equipped aircraft, but the British squadrons alone could not provide the density required. Two United States Army Air Force Liberator squadrons, NOS 1 and 2, were loaned to No. 19 Group for the duration of the operation. Their aircraft carried the American SCR-517 radar, a centimetric set comparable to the ASV Mark III, but manufactured in different factories to different standards. And their crews had trained for high-altitude daylight bombing, not low-level submarine hunting over water. The operational planners at Plymouth laid out a grid across the Bay of Biscay, a rectangle of ocean 120 miles wide and 80 miles deep, divided into lanes that the aircraft would sweep in parallel tracks. The concept demanded that 7 aircraft be airborne simultaneously during the daylight hours, flying line abreast with their radar beams overlapping to create a solid wall of electronic surveillance that no surfaced submarine could penetrate. The spacing was calculated from the detection range of the SCR-517 at 2,000 feet, which the American crews considered suicidally low for a heavy 4-engine bomber, but which the tactical instructions insisted was necessary to avoid the sea clutter that still troubled the centimetric sets at higher altitudes. Gondola launched on the 6th of February and ran for 12 days without pause. The Liberators took off from St. Ival and Predanach in Cornwall, climbed to patrol altitude over Land's End, and steered south across the grey February sea toward their assigned search lanes. The radar operators hunched over their displays in the unheated fuselages, watching the scan rotate and waiting for the bright pip that would mean a surface target. The crews were flying 10-hour sorties in aircraft never designed for low-level endurance work, the engines burning fuel at a rate that left no margin for error, the long-range tanks that would have extended their time on station still sitting in depots back in the United States. The fuel limitation meant that the Liberators could spend no more than 4 hours in the patrol area before turning for home, and the transit time across the bay consumed the rest of their endurance. The grid was never fully saturated at all hours of daylight, and the U-boats that crossed at the edges of the patrol periods slipped through the gaps. Over 12 days, the American crews flew just over 300 sorties, their radar operators gaining 19 positive contacts on surfaced submarines. That was a dramatic increase over the barren months of the METOX era, but the attacks that followed were ragged and poorly coordinated. The bomb runs made by pilots who had never trained against a maneuvering submarine. Only one U-boat was confirmed destroyed during Operation Gondola, the Type 9 C-boat U-519, caught by a No. 2 Squadron Liberator on the 10th of February and straddled with depth charges that broke its pressure hull at 200 feet. 5 other submarines were damaged, some seriously enough to abort their patrols and limp back to the Biscay ports for repairs that took weeks. The operational analysis that followed the operation was brutally frank. The centimetric radar worked, the saturation concept was sound, but the execution had been crippled by short fuel legs, inadequate crew training in anti-submarine tactics, and a patrol density too thin to seal the transit routes completely. The lessons went directly into the planning for the next offensive, which would be larger, better coordinated, and sustained for weeks instead of days. The British factories were turning out ASV Mark III sets at last in growing numbers, and the first Liberators with full long-range tankage were arriving on the Irish bases that would bring the mid-ocean gap within reach. The spring of 1943 was approaching, the weather would lift, and the Bay of Biscay was about to become the most dangerous stretch of water on Earth for a surfaced submarine. The centimetric secret was still holding. The Metox receivers on 100 U-boats were scanning frequencies that carried nothing but static, and the crews who trusted them were dying without ever knowing what had found them in the dark. The patrol rooms at Northwood absorbed the hard lessons of Operation Gondola through the final weeks of February 1943. The grid searches over the Bay of Biscay had proved that centimetric radar could find U-boats the Metox detector never heard. The problem was density. Too few aircraft had been available to saturate the transit routes and hold the submarines down. The analysts recommended a new offensive, one that would mass every available Lee Light Wellington in a single sustained hammer blow across the approaches to the French ports. The air officer commanding-in-chief endorsed the plan within days. No. 172 Squadron completed its conversion to the full ASV Mark III and Lee Light combination by the first week of March. The Wellingtons now carried the rotating dish scanner in a belly blister, feeding a plan position display to the radar operator at his console in the fuselage. The sets had been tuned and hardened through the winter. The magnetrons no longer drifted after the first hour of flight. Ground crews at Predanak and Saint-Eval learned to swap the delicate valves in under 40 minutes, keeping the patrol schedule intact. Each aircraft represented a numbered asset tracked on the operations board at group headquarters. The technique was now drilled into every crew until it became muscle memory. The radar operator would pick up a contact at 8 or 10 miles, a sharp blip on the green cathode ray screen that no German receiver could hear. He would call the bearing and range to the pilot. The Wellington would descend to 200 feet above the black water. At half a mile, the radar image dissolved into sea clutter, and the pilot pressed the searchlight switch. A cone of white light stabbed down from the belly, illuminating a circle of churning wake, and the dark cigar shape of a surfaced U-boat caught utterly by surprise. The depth charges were gone before the German gunners could even find their triggers. The Christmas Eve kill had been a solitary warning. Through the bitter weeks of March, the crews of NOS 1072 and 407 squadrons honed their night attack drills over Cardigan Bay and waited for the signal that their new weapon system was about to face its first massed trial. That trial, Operation Enclose, was scheduled for the 1st of April, a saturation offensive that would hurl 32 Lee Light Wellingtons into the Bay of Biscay in 3 sweeps every 24 hours, a solid wall of radar and light across the U-boat transit lanes. The true test of the centimetric secret lay not in isolated kills, but in whether an entire Wolfpack route could be shut down. The psychological impact on the U-boat force was immediate and corrosive. Commanders who had trusted their Biscay Cross antenna to give them 10 minutes to submerge now found themselves under depth charge attack before any alarm sounded. Boats began surfacing at night only when essential for battery charging, and even then the engineering officers kept one hand on the dive alarm. The transit through the Bay of Biscay, once a routine 3-day surface run, became a nightmare of submerged crawling at 3 knots. Batteries drained. Progress toward the Atlantic killing grounds slowed to a fraction of what the operational schedule demanded. Bijou in Berlin struggled to understand the technical shift that had stripped away their early warning advantage. Air Vice Marshal Bromet at No. 19 Group in Plymouth laid the operational framework for the next phase on a large chart table in the underground operations room. He drew a rectangle across the central Bay of Biscay, 140 miles wide and 80 miles deep, straddling the known transit routes from Lorient, Saint-Nazaire, La Pallice, and Bordeaux. The plan called for 32 Lee Light Wellingtons from NOS 172 and 407 squadrons to fly parallel track sweeps through the zone 3 times every 24 hours. The aircraft would enter the patrol area before first light to catch boats that had surfaced for a dawn battery charge. The operation was given the codename Enclose, and it would launch on the 1st of April. The scale of Enclose dwarfed anything previously attempted over water. 32 Wellingtons took off from Predanak, Saint-Eval and Chivanor in the grey pre-dawn of April 1st, forming a staggered curtain of radar coverage that swept eastward across the transit lanes. Each aircraft flew a designated track spaced 6 miles from its neighbor. The ASV Mark III scanners rotated in their belly blisters, invisible pulses washing across the wavetops every 3 seconds. The METOX receivers on the U-boat conning towers detected nothing. The boats that had surfaced to recharge their depleted batteries after a night submerged never sensed the wall of aircraft approaching until the searchlights snapped on. The first sightings came within 90 minutes of crossing the French coast. The operation ran for 8 days without pause. By the time the weather closed in on the 9th, the Wellingtons had logged 26 confirmed radar contacts and pressed home 15 attacks. U-665, a Type 7C boat commanded by Korvettenkapitän Hans-Jürgen Haupt, was caught on the surface by a No. 172 squadron crew on the third night. The searchlight illuminated the boat at 600 yards. The stick of depth charges straddled the engine room. Haupt and his entire crew of 45 went down with the boat. 5 other U-boats limped back to French ports with shattered flak platforms, ruptured fuel tanks, and crews shaken by the sudden violence that had descended from the darkness without any warning at all. The METOX had become useless. The reports reaching BDU headquarters in the Hotel am Steinplatz in Berlin painted a picture of catastrophe. Dönitz convened an emergency conference of his senior staff officers on the 12th of April. His operational doctrine, built on the assumption that U-boats could safely transit the Bay of Biscay on the surface by night and submerge only when the METOX gave warning, had collapsed. He issued a new order within 48 hours. U-boats would submerge during daylight hours and surface only at night to recharge batteries. Transit groups would be formed for mutual anti-aircraft protection. It was a desperate measure that conceded the surface to Allied aircraft for 12 hours out of every 24. The time lost to submerged crawling meant fewer boats on station and longer gaps between convoy interceptions. The effect on convoy losses was measurable within weeks. The April tonnage figures showed a sharp decline. May brought the lowest loss rate in 18 months. The North Atlantic lifeline, which had been bleeding ships faster than the yards could replace them, began to stabilize. Merchant seamen who had sailed through the black years of 1941 and 42 noticed the change in the atmosphere on the bridge. Fewer alarm bells in the night, fewer burning tankers on the horizon. The Wellingtons of No. 172 and 407 squadrons, flying their invisible radar walls across the bay, had denied the U-boats the freedom of the surface that their entire operational method required. The Kriegsmarine was being strangled in its own transit lanes. A new weapon arrived in the North Atlantic that spring, one designed to solve a problem the Lee Light could not address. The searchlight and the depth charge could kill a surfaced submarine. But a U-boat that dived in time, that got its conning tower under before the aircraft reached the drop point, was still relatively safe. The Mark 24, mine as it was called for security purposes, was not a mine at all. It was an acoustic homing torpedo built by the Americans, a compact weapon 7 feet long and weighing 680 pounds, with a 92-pound Torpex warhead and 4 crystal hydrophones mounted around its body. It was designed to be dropped ahead of a diving submarine, where it would circle and listen for the cavitation of the screws, steering itself into the target at 12 knots. The crews called it Fido, a consolidated liberator of No. 86 Squadron, operating from Aldergrove in Northern Ireland, carried the first operational Fido on the 12th of May. The crew was flying a patrol over a westbound convoy when the radar operator picked up a surfaced U-boat at 11 miles. The boat dived before the Liberator reached visual range, leaving only a swirl of white foam on the grey Atlantic. The pilot flew to the swirl and the bomb aimer released the Mark 24 from the bomb bay. The torpedo splashed into the water and began its search pattern, a slow circle spiraling downward, the hydrophone straining for the characteristic beat of diesel-electric propulsion. 30 seconds passed. Then a deep thump rolled up through the water. A plume of oil and debris broke the surface. The Liberator circled for 20 minutes. Nothing else surfaced. A U-boat had become the first victim of the homing torpedo. The tactical implications of the Mark 24 spread through the U-boat force like a cold contagion. A commander could no longer assume that diving would save him. The weapon could follow him down. The standard evasion drill of a crash dive and a hard turn under the water, which had worked against depth charges dropped by eye, was useless against a torpedo that steered itself toward the noise of the propellers. Boats began to dive earlier, at the first hint of an aircraft, sacrificing battery power and position for survival. The combination of the centimetric radar that gave no warning, the Lee light that exposed them at night, and now a weapon that hunted them underwater broke the confidence of men who had once dominated the Atlantic sea lanes. By the end of May, Dönitz faced a strategic crisis that no amount of tactical improvisation could solve. His boats were being attacked in the transit lanes, with a frequency and lethality that made the Biscay Passage a statistical gamble. The Bay of Biscay offensive, mounted by NOS 15 and 19 groups, had transformed the approaches to the French ports from a safe highway into a killing ground. Convoy losses in the North Atlantic dropped below the level that threatened Britain's survival. The crisis of the Atlantic, which had consumed the attention of Churchill and the War Cabinet through 1942, was passing. The U-boats were not defeated, but they had lost the initiative. They would never regain it. The summer of 1943 marked the end of the surface U-boat war in the Atlantic. Dönitz ordered his commanders to abandon the Bay of Biscay transit in favor of submerged passage, a slow and exhausting ordeal that halved the time a boat could spend on its patrol station. The Kriegsmarine began developing the Schnorkel, an air intake mast that would allow a submarine to run its diesels while submerged, as a desperate technological response to the radar and light combination that had swept the sea lanes. Coastal Command had achieved what the pre-war planners had only glimpsed in theory. The integration of centimetric radar, the airborne searchlight, and the acoustic homing torpedo had broken the back of the Wolfpack doctrine. The sea lanes that fed Britain were open. The Schnorkel mast rose 3 feet above the grey Atlantic swell, a thin steel tube that transformed the U-boat campaign in the final winter of the war. German boats no longer needed to surface to charge their batteries. They could cruise at periscope depth, diesels gulping air through the mast, invisible to the centimetric radars that had driven them from the surface in 1943. The Lee Light Wellingtons and Liberators of the Biscay offensive found nothing but empty water on their night patrols. Coastal Command faced a simple, brutal problem. The enemy had moved into a medium where radar could not follow him. Professor Blackett's Admiralty Committee had anticipated this moment. As early as 1942, they had pushed for an expendable acoustic buoy, something an aircraft could scatter across a suspected submarine position, and use to listen for the sound of screws and machinery beneath the waves. The US Navy conducted the first successful airdrop tests in March of that year. The production buoy, designated AN-CRT-1, entered service in June 1942 and began reaching Coastal Command squadrons in quantity soon after. The crews called it by the colors painted on its 6 radio channels: purple, orange, blue, red, yellow, and green. The acronym POBRIG became the shorthand for a revolution in underwater warfare. The buoy itself was a cylinder just under 3 feet long, packed into a small parachute that controlled its descent. On hitting the water, a flotation chamber inflated, a hydrophone unspooled on a cable, dropping to a preset depth. The transmitter on the surface sent everything the hydrophone picked up directly to the aircraft circling overhead. Each buoy operated on a different radio frequency, color-coded for the operator hunched over his receiver in the fuselage. He cycled through the channels one by one, pressing his headphones tight against the drone of the engines, listening for the rhythmic beat of submarine propellers. The standard search pattern was a 5-buoy cross. The navigator dropped the first buoy on the last known position of the submarine, the datum. The pilot then flew the aircraft to positions 2,500 yards north, south, east, and west of that point, the crew releasing a buoy at each. The sonics operator began his scan, reporting signal strength in a quiet, level voice over the intercom. Strength 5 meant the submarine was within 500 yards of that buoy. Strength 4, within 1,000. The navigator plotted concentric circles on his chart. Where the arcs intersected, the target lay. The system was crude by any measure. The buoys were non-directional. They could tell you a submarine was close to a particular buoy, but not whether it lay to the left or right, ahead or astern. Signal strength gave only an approximation of range. The ocean played constant tricks with the sound. Thermal layers bent the acoustic energy downward, hiding a submarine completely from the hydrophone dangling at the wrong depth. The operator heard biological noise, shrimp clicking, the groan of distant ships, the hiss of waves. Discerning the thin, high whine of electric motors from the background required hours of practice and an ear for pattern. The operational effect was immediate and corrosive to the German submarine force. A snorkeling boat could now be detected, tracked, and attacked without ever breaking the surface. The old tactic of diving to escape had become a trap. Barrier patrols between Iceland and the Faroes evolved into coordinated air submarine killing zones. Maritime patrol aircraft saturated the gaps with radar, forcing the U-boats under. Allied submarines waited below, listening passively for the diesel roar of a boat on schnorkel. The sonobuoy closed a loop that had been open since 1917. The war ended, but the submarine threat did not. By the late 1940s, the Soviet Union was building a new generation of ocean-going boats, based on captured German Type 21 technology. These were true submarines, faster underwater than on the surface, capable of staying submerged for days. Coastal Command needed a new aircraft to replace the war-weary Sunderlands and Halifaxes. The piston engine and the flying boat hull had reached their practical limits. The requirement, issued in 1946, called for a land-based platform with the endurance to patrol the Greenland-Iceland-UK gap and the sensor suite to find whatever lurked beneath it. The Avro Shackleton materialized from the Lancaster bomber, but it was a very different aircraft. The fuselage was widened and deepened. The wings stretched to 120 feet. 4 Rolls-Royce Griffon engines, each generating over 2,000 horsepower, drove contra-rotating propellers that pulled the aircraft through the air with a distinctive growl, audible for miles. The crew of 10 operated in an unpressurized cabin for up to 18 hours at a stretch. 2 pilots, 2 navigators, a flight engineer, and 5 signalers packed into a narrow aluminium tube suspended over the North Atlantic. The Shackleton Mark I entered squadron service in 1951. It carried the ASV Mark 13 radar, a centimetric set with a rotating scanner housed in a ventral radome behind the bomb bay. The sonobuoy processing equipment occupied a rack in the main cabin, where the signalers sat facing inward, their backs to the fuselage wall. A magnetic anomaly detector boom extended from the tail, a long stinger that sensed the distortion in the Earth's magnetic field caused by a steel submarine hull. The integration of radar, sonics, and magnetic detection on a single platform was something new in maritime warfare. The Shackleton did not simply locate submarines. It fused data from 3 separate sensor systems into a single tactical picture. The weapon load reflected the hard lessons of the Atlantic campaign. Twin 20mm cannon in the nose gave the aircraft a punch against surface targets. The bomb bay could carry depth charges, sonobuoys, and marine markers. But the primary weapon was the Mark 30 torpedo, a passive homing weapon that tracked the cavitation and machinery noise of a submerged submarine at 30 knots. It was heavier, faster, and smarter than the wartime Fido. The kill chain that had begun with a searchlight and a depth charge in 1941 was now a fully instrumented process. The aircraft had problems of its own. The Griffon engines were complex and thirsty. Maintenance hours per flight hour ran high. The contra-rotating gearboxes required constant inspection. In the unpressurized cabin, temperatures dropped below freezing at operational altitude. Crews wore immersion suits from takeoff to landing, the rubber fabric cold and stiff against the skin. The 2 navigators worked at separate chart tables, one managing the geographical navigation, the other controlling the tactical picture from the sonics and radar stations. The flow of information between them, passed by intercom and penciled notes, was the human nervous system of the machine. The Shackleton force replaced the Sunderlands of the wartime flying boat squadrons one by one through the early 1950s. It became the backbone of Coastal Command's maritime patrol capability, operating from bases at Kinloss in Scotland, St Morgan in Cornwall, and Ballykelly in Northern Ireland. The mid-Atlantic gap was finally closed. A Shackleton could fly 1,000 miles into the ocean, spend 6 hours on patrol, and return to base with fuel in reserve. The coverage that had required a carrier task force in 1942 now came from a single land-based aircraft. The Pobrig sonobuoy system had a fundamental limitation. It could tell a crew that a submarine was in the water. It could not tell them precisely where. The non-directional buoy gave only signal strength, a rough proxy for range, and nothing for bearing. An experienced operator could detect Doppler shift as the submarine passed the buoy, a rise and fall in frequency that indicated relative motion. But this required the aircraft to fly a precise pattern, while the navigator plotted the changing tones. In the rough weather of the North Atlantic, with Soviet submarines growing faster every year, this was not good enough. The answer came from a British design program that ran parallel to the American Pobrid series. The Type C sonobuoy was a directional device, large enough to require bomb bay carriage rather than hand launching. Inside its cylindrical casing, a directional hydrophone array rotated slowly, sweeping the water column for acoustic energy. The buoy transmitted not just the sound of the submarine, but the bearing from which that sound arrived. In the aircraft, a cathode ray tube displayed the bearing as a line on a screen. The operator could watch the submarine move relative to the buoy in real time. The Type C system entered service in 1959, coupled to the Shackleton's Mark 1C Sonics processing suite. The combination of passive directional buoys with an active mode created something entirely new. The active buoy worked on the principle of explosive echo ranging. A small charge detonated at a known depth. The shockwave radiated outward, struck the submarine hull, and returned as an echo. Directional hydrophone measured the bearing of the returning sound. The time delay between detonation and echo gave the range. The system triangulated the target with an accuracy measured in tens of yards. The operational technique was taught as a drill at the Joint Anti-Submarine School at Londonderry. The Shackleton crew would lay a field of directional buoys in a precise geometric pattern. The navigator, now acting as tactical coordinator, plotted each buoy position on his chart. The Sonics operator called bearings as they appeared on his screen. The navigator drew the bearing lines back from each buoy position. Where the lines crossed, the submarine lay. The aircraft then turned inbound on an attack heading, the pilot reducing height to 500 feet, the weapon bay doors opening. The detection range tripled, where the old pobrig pattern required the submarine to be within 2,500 yards of a buoy to achieve a fix. Directional system could track a target at ranges of 4,000 yards or more in favorable water conditions. The aircraft no longer needed to fly directly over the submarine to localize it. This had two immediate tactical consequences. The submarine commander received less warning of the attack, and the aircraft could remain at a higher altitude, conserving fuel and expanding its search area. There remained a crucial distinction. The Type C system was a localization system, not a detection system. It required the crew to have some prior indication of the submarine's presence, a radar contact, an intelligence report, or a visual sighting of a periscope feather. The buoys refined that initial cue into a precise weapon release point. The hope of a system that could sweep vast ocean areas for submarines without any prior cue remained unrealized. The search problem, the needle in the haystack, persisted. The jet engine transformed every aspect of military aviation except one: endurance. A jet burns fuel at a rate that makes long patrols problematic. The solution, when the air staff began planning a Shackleton replacement in the early 1960s, was to adapt the de Havilland Comet airliner. The Hawker Siddeley Nimrod first flew in 1967 and entered squadron service 2 years later. 4 Rolls-Royce Spey turbofans slung under a low-wing fuselage gave it a transit speed of 500 knots, 3 times that of a Shackleton wallowing through a headwind. The Nimrod carried the Searchwater radar, a high-power centimetric set with a digital processing back-end that could discriminate a periscope from wave clutter in conditions that would have blinded the old ASV sets. The integrated mission computer accepted inputs from the radar, the sonobuoy receivers, the magnetic anomaly detector, and the electronic support measures that sniffed for submarine radar emissions. The computer fused the data streams into a single tactical display. The human operator still made the decisions. The machine organized the information so he could make them faster. The weapon bay held 9 Mark 46, or Stingray anti-submarine torpedoes, each a self-contained homing weapon with its own active sonar seeker. Wing hardpoints carried Sidewinder missiles for self-defense and Harpoon or Sea Eagle anti-ship missiles for the surface strike role. The Nimrod could hunt submarines and attack surface ships on the same sortie, switching roles with a flick of a selector switch. The crew of 12 pilots, 2 navigators, a flight engineer, an air electronics officer, and 6 air electronics operators managed the systems in shifts on the long patrols. The navigator had evolved from the man with a Dalton computer and a sextant into the tactical coordinator of a networked weapon system. He sat at a console in the darkened tactical compartment, surrounded by screens and controls, managing the search pattern while the computer processed sensor data in the background. The dual navigator crew concept carried over from the Shackleton. The first navigator handled the geographical problem, the second the tactical one. On a 10-hour patrol, they would swap positions to maintain alertness. The captain, often a senior navigator rather than a pilot, orchestrated the whole crew through the intercom. The Nimrod embodied every lesson Coastal Command had learned since 1939. The radar descended directly from the cavity magnetron that Randall and Boot had produced in their Birmingham laboratory. The Sonobui processing software encoded the Doppler analysis techniques that wartime operators had worked out with pencil and paper. The magnetic anomaly detector in the tail boom was a direct descendant of the Madgear that Catalinas had flown over the Straits of Gibraltar in 1944. The integrated mission computer automated what the navigator of a Lee-Light Wellington had done by instinct and dead reckoning. A Nimrod on patrol over the Greenland-Iceland-UK gap in the winter of 1969 flew a pattern that would have been recognizable to the crew of a Sunderland in 1940. The aircraft cruised at low altitude, radar scanning the sea ahead, sonobuoys ready in the launchers. The electronics operators monitored their screens in the dim blue glow of the tactical compartment. Outside, the North Atlantic heaved in the same grey swells that had hidden U-boats and their hunters for 3 decades. The difference lay in the data streaming through the computers, the fusion of sensors that gave the crew a picture of the underwater battle space their predecessors could only have imagined. The institutional DNA of Coastal Command survived long after the command itself was absorbed into RAF Strike Command in 1969. The operational techniques taught at the Joint Maritime Course at RAF Turnhouse, the Sonobui patterns standardized in NATO tactical publications, the kill chain from detection to weapon release, all traced their lineage back to the squadrons that had fought the Battle of the Atlantic with obsolete Ansons and improvised depth charges. The Shackleton soldiered on until 1991. Outlasting the Soviet Navy, it was designed to counter. One aircraft, MR2, WR963, remains under preservation at Coventry Airport. A Nimrod MR2 stands at the Yorkshire Air Museum. The airframes are silent now. The techniques they pioneered remain doctrine. Edward Brooks remained in the RAF, retiring as a wing commander in 1955. W.W. Campbell, awarded the DFC, continued flying until his death in a flying accident in 1947. W. Gibson transferred to the Royal Australian Air Force and later became a civil pilot. Sir Frederick Bowhill served as Air Officer Commanding-in-Chief Coastal Command until 1941, retiring as Marshal of the Royal Air Force. Sir Philip Joubert de la Ferte held several senior Air Ministry posts before his own retirement in 1947. If you served on Shackletons, Nimrods, or any of the Coastal Command aircraft described in this series, or if a family member flew those long grey patrols over the Atlantic, we would be honored to hear your story in the comments below. Your memories are the living archive of this history. Please subscribe to the channel and give this video a like. Your support keeps these documentaries coming. Thank you for watching.